Hello students, welcome to Sujia Chem classes. After a gap of nearly 3 weeks, I am bringing out a video for class 11 students based on Unit 2, Structure of Atoms. You may consider it as part 1. This part 1 comprises of 15 questions. It would be not only helpful for class 11 students but also for class 12 students who it will act as a practice session for them. They can go through the questions, practice them. It would help them in any of the forthcoming entrance examinations which they are going to face. So let's begin with the question answer discussion from the unit Structure of Atom. Question number 1. Which is the correct order of increasing number of unpaired electrons in the following ions? 4 ions are given: Cr2 plus, Sc3 plus, Ni2 plus and Fe3 plus. Along with these ions, within brackets, the atomic numbers of the elements are given. It's not the atomic number of the ion, the atomic number of the elements: chromium, scandium, nickel and iron are given. 4 options. You need to select the right option. So let's get to the answer. Before deciding the number of unpaired electrons, we must have a thorough knowledge of the electronic configuration of these transition metals. For chromium with atomic number 24, its electronic configuration is 3d54s1. Scandium Sc 3d14s2. Nickel 3d84s2. Iron 3d64s2. Now, from these elements, atoms of these elements, we need to knock out electrons. Whenever you do so, whenever you remove electrons, care should be taken to remove the electrons from the outermost shell first, the orbitals present in the outermost shell. So here the outermost shell is the 4th shell, and the electrons first need to be knocked away from the s orbitals, and then if there are more electrons to be removed, they should be removed from the 3d orbitals. So the electronic configuration of Cr2 plus reduces to 3d4 4s0 with 4 unpaired electrons. Scandium 3 plus 3d0 4s0, 0 unpaired electrons, no unpaired electrons. Ni2 plus 3d8 4s0, number of unpaired electrons 2. Fe3 plus 3d5 4s0, number of unpaired electrons 5. Therefore, Fe3 plus has the maximum while Sc3 plus has minimum number of unpaired electrons. So correct increasing order would be B, C, A, last is D. So D highest number of unpaired electrons, B lowest number of unpaired electrons. Option 4 is the right option. Question number 2. Niels Bohr was the first scientist to explain quantitatively the general features of the structure of hydrogen atom and its spectrum. Now the question is, if the energy of an electron in the third orbit is minus E3, it's given in the problem that the energy of the electron in the third Bohr's orbit is minus E3. What would be the energy of an electron in Bohr's first orbit? Now, what are these orbits? Orbits, according to Bohr's model of an atom, are the circular paths, paths, which the electron takes while moving around the centrally placed nucleus. So the circular paths are labeled as K shell, L shell, M shell, N shell, etc. For K shell, the N value, the number of the orbit is 1. Similarly, for the L shell, it's 2, then M shell, it's 3, etc. Then, to answer this question, we need to know one feature of Bohr's atomic theory, that is, the energy of an electron in an orbit, if it is En, n can be 1, n can be 2, 3, anything, the number of the orbit. So En is proportional to 1 by n square, where n is the number of the orbit in which the electron is present. So therefore, E1 would be proportional to 1 by n square, which is 1. So 1 square. E1 would be proportional to 1 by 1, and E3 would be proportional to 1 by 3 square. That is the energy of the third orbit. E square 3 square. So 3 square is 9. But it is given that the energy of the third orbit is minus 3. So we write it as minus 3 is proportional to 1 by 9. Therefore, finding out E1 by the ratio E1 by minus E3 is equal to 9 by 1. How 9 by 1? 1 divided by 1 by 9, which is 9 by 1. Or E1 is equal to minus E3 into 9, or minus 9 E3. Therefore, if you look at the options, option C is the right answer. Here I have given a diagrammatic representation of Bohr's model of an atom, that is hydrogen atom, with the nucleus and the various circular orbits in which the electron can travel round the nucleus. Question number 3. According to quantum mechanics, an orbital is a region in space around the nucleus where there is maximum probability of finding an electron. Now, what would be the total number of atomic orbitals in the fourth energy shell of an atom? Options are given, 4 options, and we need to arrive at the right option. Now, before we go into the answer, I want the students to have a clear cut idea about what is a shell, a subshell, and an orbital. What is the need to have a subshell and an orbital? Now, let us discuss that first in a nutshell, very short form. In an atom, shells are energy levels. They are energy levels characterized by, defined by principal quantum number n, and they denote regions of space around the nucleus where there is high probability or maximum probability of electrons being found. So that's what is a shell. Each shell has a quantized energy value. A quantized energy value means its energy will not vary continuously. Energy is quantized. If an electron is present in a shell, its energy is quantized. It cannot have different energy values within the shell. It will have the same energy value. Now, shells which are closer to the nucleus have lower energy values, and as these shells go further away from the nucleus, they get to have higher quantized energy values. Now, coming to what is a subshell. Each shell is further subdivided, is further divided into subshells. These subshells are these subshells are denoted by or defined by, characterized by azimuthal quantum number L, azimuthal quantum number L, or subsidiary quantum number L. And now, what do these subshells denote? These subshells denote the shape of the region where there is region around the nucleus where there is maximum probability distribution of an electron around the nucleus. Now, subshells are of four types: the S subshell, P subshell, D subshell, and F subshell. S, P, D, and F subshells. What are they? They are regions of space which have different shapes. For example, the S subshell is found to be spherical in shape, whereas the P subshell is dumbbell shaped. D subshells have two dumbbells together, joined together, and F subshells have complicated shapes. So that is about a subshell and how they are characterized by azimuthal quantum number L value. Now, within the subshell, we have what are called as orbitals. Orbitals denote the region in space around the nucleus where there is high probability of an electron being found. Now, what is the difference between a subshell and an orbital? A subshell does not give any information about how this spherical s orbital is oriented, distributed along the x, y, and z axis. Similarly, subshell P does not indicate how the dumbbells are oriented, distributed along the different x, y, and z axis. So also in case of d and f orbitals. F orbitals, if you consider not d orbitals, d subshells. D subshells do not the D subshells do not talk about how these subshells are oriented, distributed in space along the x, y, and z axis. So, for that, we need to have another quantum number which is called as magnetic quantum number. This magnetic quantum number small m, denotes how a subshell, an S subshell, gets oriented in space. If you look at the S subshell, it is symmetrically distributed, uniformly distributed along the X, Y, and Z axis. So that's why we say S subshell is symmetrically distributed. Hence, this S subshell is now called as S orbital. So, an orbital is within the subshell, showing how these spherical orbitals get distributed along the three axes. Hence, an orbital is not only defined by L value but also by M value. If you consider the s orbital, because it is spherically distributed, there is only the possibility of one s orbital. But if you consider dumbbells, p orbitals, they are of three types. The dumbbells can be oriented along the x-axis. then it's called as px orbital. Along the y-axis, it is then known as py orbitals, and along the z-axis, it will be called as pz axis. See how the regions in space are now getting specific terms depending upon how they are distributed in space. If you look at the d orbitals, the d orbitals are 5 in number because of the varying directions, orientations in space around the nucleus. Two of the d orbitals are oriented along the axis x and y axis or z axis, while three of the d orbitals point in between the axis xy axis or yz axis or xz axis. If you look at the f orbitals, based on their orientation along the different axes x, y and z, they are 7 in numbers. So, if you now come to the answer, it is given that the principal quantum number value of the energy level is 4. So, the possible azimuthal quantum number values would be 1 less than the azimuthal quantum number values are always restricted by the principal quantum number value. So, subsidiary or azimuthal quantum number values are 0, 1, 2 and 3. The corresponding orbitals are given as, if L, the azimuthal quantum number value is 0, then it denotes a subshell and an s orbital. This s orbital would be 1s orbital. The s orbital would be 4s orbital. 4s orbital, and there is only one type of 4s orbital. Then if L is equal to 1, it denotes p subshell with three different types of p orbitals: 4px, 4py, 4pz. Similarly, we have when L is equal to 2, it denotes d orbitals. The d orbitals in the fourth shell, they may be filled with electrons, they may not be, but there are 5 different types of d orbitals: dx square minus y square, dz square, dxy, dyz and xz. So that is 5 different types of d orbitals. Now when L is equal to 3, it denotes f subshell, and there are 7 different types of f orbitals within this subshell. So 7 plus 5 plus 3 plus 1, total is 16. So total number of orbitals in the fourth shell would be 16. Therefore, option B is correct. The next two slides denote the different shapes of orbitals. Say, for example, in the first slide taken, 1s orbital, look how it is spherically symmetrical. The sphere is symmetrically distributed along the x, y and z axis. Now coming to the p orbitals, see how the lobes get oriented along the axis, either x axis or y or z axis. Accordingly, you will have 2px, 2py and 2pz orbitals. Coming to the d orbitals, if you notice dz square and dx square minus y square orbitals, d orbitals, they have the dumbbell's lobes oriented along the axis, whereas dxz, dyz and dxy have lobes of the dumbbells in between the axis. So there are 5 different types of d orbitals, each with the same n L values but different m magnetic quantum number values. The next slide shows complicated shapes of the f orbitals. Coming to next set of questions 4, 5 and 6. Question number 4 and 5 deal with de Broglie's equation, relation. Question number 4, let us take question number 4 first. All subatomic particles show a dual nature, particulate nature and wave nature, just like the radiations. Here I would like to give a small explanation. Subatomic particles mean particles having very negligible mass, like an electron, a proton, an ion, an atom, a molecule, etc. So such particles which are subatomic, microscopic, show particulate, particle-like and wave-like nature. Just like radiations means just like light radiations. In case the particle becomes massive or it has a large mass, for example, a grain of sand, a small grain of sand is considered to be massive. A grain of rice, a pebble, these are all massive particles. In case of particles having large mass, their wave nature becomes insignificant while they exhibit particulate nature. This is in case of particles or matter having large mass. If any form of matter is found in the form of subatomic particles, then they will exhibit a dual character, wave-like and particle-like. Now, coming to the question, what would be the ratio between the wavelength of an electron and a proton if we suppose that the proton is moving with 1/4 the velocity of the electron? Given mass of electron is 9.11 into 10 power minus 31 kilogram and mass of proton is 1.67 into 10 power minus 27 kilogram. Using de Broglie's relation, we can find the ratio between lambda E and lambda P. We know that lambda is equal to h by mv, where h is the Planck's constant. So we write out the equation for lambda E in case of electron. Lambda E is h by MeVe, where Ve is the velocity with which the electron is moving, and lambda P is the wavelength of the proton, which is equal to lambda P is equal to h by mp Vp. Mp is the mass of the proton, Vp is its velocity. Finding the ratio lambda E by lambda P is equal to mp Vp divided by me into Ve, the whole into 1 by 4. How did we get 1 by 4? Because it is given that velocity of proton is 1/4 the velocity of the electron. So therefore, Vp by Ve becomes equal to 1 by 4. Therefore, we get lambda E by lambda P is equal to 1.67 into 10 power minus 27 into 1 into 1 by 4, the whole thing 1 by 4. This is divided by 9.11 into 10 power minus 31. So the ratio between the mass of proton by mass of electron into 1 by 4, that is found to be 458. So lambda E by lambda P is 458. Next, given below are 4 subatomic particles traveling with the same velocity v. Which of them will have the shortest wavelength? Lambda value, which one will have the lowest value? The particles are A proton, B neutron, C alpha particle. Alpha particle is positively charged helium ion. Positively charged helium ion. Meaning this alpha particle has 2 electrons knocked away. So it is 2He4. The mass of this particle is 4 atomic mass units. And electron, you know the mass of electron, proton. Neutron is having a mass almost the same as that of the proton. So, for this also, to arrive at the answer, we use de Broglie's relation. We know that lambda is equal to h by mv. Velocity for the 4 particles is found to be the same, and h is the Planck's constant. So the equation finally reduces to lambda is equal to 1 by m for all the 4 particles. Now, that means lambda is inversely proportional to the mass of the particle. Since alpha particles have the largest mass among these 4 particles, its wavelength would be the shortest. It would have the shortest wavelength. Therefore, if you look at the options, option C is the right answer. Alpha particles will have shortest value of wavelength. Coming to question number 6. This question deals with Bohr's orbit, or we can also call these orbits as stationary state or energy state. I have given 3 names: Bohr's orbit, or stationary state, or energy state. Stationary. Why stationary? Because according to Bohr, if an electron is present in an orbit, it will have its energy will not change. That is the meaning of stationary state. So let's take the question. Which stationary state in Be3 plus tripositive beryllium ion will have the same energy as the third energy state of hydrogen atom? Options are given. We need to arrive at the correct answer. For this, we have to know the energy of the stationary state of hydrogen, or the energy of the orbit of hydrogen. It is given as EH is equal to minus RH into 1 by n square joules. That's the energy of the electron in a stationary state in hydrogen atom. Now, what is RH? RH is called as the Rydberg's constant, and its value is equal to 2.18 into 10 power minus 18 joules. Therefore, EH, the energy of an orbit in the hydrogen atom, is given as minus 2.18 into 10 power minus 18 into 1 by n square joules. What is n? The number of the orbit or the stationary state. So, for other ions having one electron like hydrogen atom, meaning all other one electron species, the energy of the nth stationary state, any stationary state for such one electron species, is given by the expression En is equal to minus 2.18 into 10 power minus 18 into Z square by N square. Now, what is Z? Z is the atomic number of the one electron species. Example of one electron ions are He plus, Li2 plus, Be3 plus. Now in the question it is asked, which stationary state in Be3 plus will have the same energy as the third energy state of hydrogen atom. So for Be3 plus we can find the value of n, the n orbit. It can be written as En is equal to minus 2.18 into 10 power minus 18 into 1 by 3 square. That is the 1 by 3 square. This is the energy value of hydrogen atom in the of an electron of hydrogen atom in the third orbit. N value is given in the problem as 3. So for hydrogen atom, if an electron is there in the third orbit or third energy state, its energy would be equal to minus 2.18 into 10 power minus 18 into 1 by 3 square, substituting n as 3. That will be equal to minus 2.18 into 10 power minus 18 into z square by n square for beryllium, that is 4 square by n square. For beryllium, Z is equal to 4. We don't know the value of n, the nth energy state or stationary state of beryllium 3 plus, which has the same energy as the third energy state of hydrogen atom. So calculating, we get n square is equal to 4 square into 3 square, or n is equal to 4 into 3, 12. Hence 12th energy level in Be3 plus will have the same energy as the third energy level of hydrogen atom. Hence option D is the correct option. Question number 7. A statement of assertion followed by a statement of reason are given. Choose the correct answer out of the following options. First, we'll see the options. Option A, both assertion and reason are correct, and reason is the correct explanation of assertion. B, both assertion and reason are incorrect statements. C, assertion is correct but reason is wrong. D, assertion is wrong but reason is the correct statement. Now, coming to the assertion statement, energy of 2s orbital of hydrogen is less than the energy of 2s orbital of lithium. Remember, lithium is a metal or element with higher atomic number than hydrogen. Atomic number than hydrogen. Z value is higher. Now, once more, assertion statement. Energy of 2s orbital of hydrogen is less than energy of 2s orbital of lithium. Reason. Energies of orbitals in the same subshell decrease with increase in atomic number. Energies of orbitals in the same subshell decrease with increase in atomic number. What does it mean? If you have an orbital in hydrogen, which is a 2s orbital, and you have the same 2s orbital in lithium, then energy of hydrogen atom is more than the energy of the 2s orbital of hydrogen is more than the energy of 2s orbital of lithium or beryllium, because they have higher atomic number. That is the meaning of that reason statement. Now look at the no, we don't have to see the options now. Let's get straight to the answer. We know that as atomic number increases, the total energy of electrons present in the same subshell I had already explained what is a subshell and orbital. So the total energy of electrons in the same subshell becomes more negative as per the equation En, electron energy, is equal to, or energy of the subshell is equal to, minus 2.18 into 10 power minus 18 into z square by n square. You have come across this equation in the last question itself. So therefore, energy of 2s orbital of hydrogen would definitely be greater than the energy of 2s orbital of lithium. Hence, energies of orbitals in the same subshell decrease with increase in atomic number. So, our assertion and reason statements, if we look at them, assertion is the wrong statement given, but reason is correctly stated. So, option D is the right choice. Now, the same taken the figure from NCERT textbook, where the energy level diagram for hydrogen is depicted as A and the energy level diagram for multi-electron atoms is shown as B. Now, if you look at 1s and 1s orbitals for hydrogen and multi-electron atoms, it's at the same level. Now, look at the 2s orbital of hydrogen. Same subshell is s orbital. Same subshell of lithium is s orbital. Look at the position of the 2s orbital. Increasing energy I've shown by a blue arrow. So look at the 2s orbital position of hydrogen and that of a multi-electron species. Which is higher? Definitely the energy of 2s orbital of hydrogen is higher in energy, less negative than the 2s orbital of multi-electron species. Yet another interesting feature of this diagram is, look at the 2s and 2p energies of the hydrogen atom. Though they have different azimuthal quantum number values, S azimuthal quantum number value is L equal to 0. For P azimuthal quantum number values, L is equal to 1. Yet, look at the energy level diagram. Both have the same energy for hydrogen atom. But if you look at multi-electron species, say for example lithium, helium, beryllium, etc. Look at the positions. The energy of 2p orbital is higher than that of 2s orbital, or energy of 2p subshell is greater than 2s subshell. Instead of talking about orbital, you can also talk about the subshell. So 2p subshell has higher energy than 2s subshell for multi-electron atom. But 2p subshell has the same energy as 2s subshell for hydrogen atom. Similarly, look at this 3s, 3p and 3d. For hydrogen, they have the same energy value. Whereas in case of multi-electron atom, see the difference in energy values. 3s subshell lower in energy, then comes 3p, then comes 4s, then comes 3d. So please look at this diagram and study this diagram carefully. It is given in the NCERT textbook. Question number 8. A stone having a mass of 40 grams when catapulted has a speed of 30 meters per second. If the speed can be measured with an accuracy of 4%, what would be the uncertainty in measuring its position? H. Planck's constant is given 6.626 into 10 power minus 34 kilogram meter square per second. 4 options are given. Now, this problem is an application of Heisenberg's uncertainty principle. Directly use the formula and arrive at the answer. Here, H Planck's constant is given in kilogram meter square per second. So, the mass of the stone which is catapulted is 40 grams. That needs to be converted to kilograms. So 40 into or 40 divided by 10,000, which is 40 into 10 power minus 3 kilogram. Heisenberg's uncertainty principle equation. Delta x into m delta v is equal to h by 4 pi, where delta x is the uncertainty in its position and delta v is the uncertainty in its velocity or speed. M is the mass of the stone. H is Planck's constant, pi is 22 by 7 or 3.14. Now, in this case, the uncertainty in speed is 4% of 30, that is 4 by 100 into 30 or 1.2 meter per second. The value 1.2 meter per second for delta V indicates that it is a high value. The uncertainty is large. Okay, let us calculate delta x. So, from Heisenberg's uncertainty principle equation, delta x is equal to Planck's constant divided by 4 into pi into mass of the stone into delta V. So substituting the values, 6.626 into 10 power minus 34 divided by 4 into 22 by 7 is 3.14 into 40 into 10 power minus 3, that is the mass, into delta V is 1.2. We get the answer as, after working out, we get it as 1.099 into 10 power minus 33 meter. It's a small amount, small number. That means the uncertainty in the measurement of its position is accurate. Uncertainty is very low. That means certainty is high. So, when the uncertainty in the measurement of position is very low, it means that it will lead to the uncertainty in the measurement of its velocity would be high, or the accuracy with which the velocity is measured. The accuracy with which the velocity is measured would be low. Okay, so if 1 is high, delta x is high, delta v will be low. If delta v, uncertainty in the measurement of its velocity or speed, is low, delta x would be high. So correct option is C. Question number 9. Which one of the following electronic jumps from higher energy levels of He plus monopositive helium to its lower energy levels will have minimum wavelength? 4 options are given, that is from n equal to energy level 3 to n equal to 1. B, n equal to 4 to n equal to 2. N equal to 4 to n equal to 1. N equal to 2 to n equal to 1. In which of these following cases, when the electron makes a transition back to the lower energy state, will the wavelength of light emitted be minimum? So, for this, we need to make use of the equation, mathematical expression, delta E is equal to h nu. since nu is equal to c, nu is the frequency of light radiation, h is Planck's constant, delta E is the energy difference between the two energy levels, c is the velocity of light, and lambda is the wavelength of light emitted. So instead of nu frequency, we can substitute as c by lambda. Therefore, delta E is equal to h into c by lambda, or lambda is equal to h into c by delta E. So here c is the velocity of light. Now, this equation reduces to, in other words, lambda is inversely related to delta E, meaning greater the delta E value, lower will be the wavelength of light emitted. So from the options, we need to choose that option which will have large delta E value. That is possible when the electron makes a jump from n equal to 4 to n equal to 1. Since in that case, delta E will be energy of the fourth energy level minus that of the first energy level. The delta E value in this case would be maximum, since the electron is making a transition, a jump from n equal to 4 to n equal to 1. Therefore, lambda will be minimum. See the inverse relation between lambda and delta E. Therefore, option C is the right answer. Question number 10. An ion X2 plus dipositive ion has a mass number of 56 AMU. Mass number means atomic mass. It has 25.01% more neutrons than electrons present in it. Deduce the number of electrons, protons and neutrons in the ion X2 plus. Four options A, B, C and D are given, where the number of electrons, protons and neutrons are given. We need to choose the correct option. Now, in this case, it is given that X2 plus carries, X2 plus is the ion. Therefore, it carries 2 units of positive charge, in the sense that it has lost 2 electrons. So, it will have 2 electrons less than the number of protons. So, let us assume that the number of electrons is X. In that case, the number of protons would be X plus 2, because it is a dipositive ion. So the number of protons is 2 more than that of the number of electrons which we have assumed as X. Now, coming to the number of neutrons. The number of neutrons, it is stated in the problem that it has 25.01% more neutrons than electrons. So, the number of electrons is X. So, 25% more of X is present as neutrons. So, the number of neutrons would be X plus 25.01x by 100. X plus 25.01x divided by 100, because that is the percentage, isn't it? So that becomes equal to 1x plus 0.2501x or 1.2501x. That is the number of neutrons in the dipositive X2 plus ion. So now total number of protons and neutrons, because atomic mass is given. So total number of protons and neutrons is 1.2501x number of neutrons plus x plus 2, that is the number of protons present in it, is equal to 56 the mass number of x2 plus. On simplifying, we get 2.2501x is equal to 54. Therefore, x is equal to 54 divided by 2.2501, which is 23.999. Within limits of experimental error, it can be taken as 24. Therefore, number of electrons, x for us is the number of electrons, is equal to 24. Number of protons is equal to 24 plus 2, x plus 2, 26. And number of neutrons would be total number of particles in the nucleus, atomic mass, which is 56, minus the number of protons. How many protons? 26. So 56 minus 26 is 30. Therefore, number of electrons 24, protons 26, neutrons 30. So option B is the right option. Question number 11. An accelerated electron has a speed of 5 into 10 power 6 meter per second with an uncertainty in speed of x percentage. The uncertainty in finding its location while in motion is 5.8 into 10 power minus 8 meter. Find x. What is x? Uncertainty in its speed. That is, if we find x, we can find the percentage. Given mass of electron is 9.1 into 10 power minus 31 kilogram. H is 6.63 into 10 power minus 34 kilogram meter square per second. This problem is also based on Heisenberg's uncertainty principle, but with a slight twist. That is all. Once we find out the uncertainty in velocity, we need to find out the percentage uncertainty in velocity. That's it. So, given that speed of the electron is 5 into 10 power 6 meter per second and uncertainty in its position is given as 5.8 into 10 power minus 8 meter. H, Planck's constant value is given, mass of the electron is given. Let the speed in uncertainty in its speed is x percent. Now, using Heisenberg's uncertainty principle equation, delta x into m delta v is h by 4 pi. We can calculate delta v, which is the uncertainty in the speed or velocity of the electron. Delta v is equal to h by 4 into pi, which is 3.14 into mass of the electron into delta x uncertainty in position. Substituting all the values, we get delta v as 0.01 into 10 power 5 meter per second. Delta v is 0.01 into 10 power 5 meter per second. Now, when the speed of the electron is 5 into 10 power 6 meter per second, then delta v is 0.01 into 10 power 5 meter per second. So, if the speed, we have to find the percentage. So, if the speed is 100 meter per second, then what would be delta v? That delta v is only given as x percent. So that x is equal to 0.01 into 10 power 5, which is delta v into 100 divided by 5 into 10 power 6. So the delta v value is 0.01 into 10 power 5 meter per second when the speed is 5 into 10 power 6 meter per second. So if the speed is 100 meter per second, what would be delta v? That is x percent, which is uncertainty in speed, which we are asked to calculate. That is equal to, after simplifying, we get 1 by 5 into 10 power minus 1. 1 by 5 is 0.2. So 0.2 into 10 power minus 1 is 0.02. So 0.02% is the value of x. Question number 12. Four quantum numbers labeling four electrons are given below as P, Q, R, and S. Which one of the following options shows the correct increasing order of their energies? The electrons are P, Q, R, and S. These are designated by N, principal quantum number; L, azimuthal quantum number; M, magnetic quantum number; and MS, spin quantum number. So there are four electrons labeled by four quantum numbers. We need to choose from the options given the correct increasing order of their energies. So let's go to each one of those. P, electron P with quantum numbers n equal to 3, L equal to 2, M equal to 1, and MS is plus half. This denotes, wherever L is equal to 2, denotes a d orbital with principal quantum number 3. So it's 3d orbital electron. Q with quantum number n is 4, L is 1, M is 0, MS is plus half. That is the spin of the electron. So this L is equal to 1 denotes p orbital. So it's 4p orbital electron. R with quantum number n equal to 4, L equal to 2, M equal to minus 2, MS equal to minus half. If L is equal to 2, we know it denotes, if L is equal to 2, it denotes d orbitals, and that d orbital is in the fourth shell. So it denotes 4d orbital electron. S electron with quantum numbers n equal to 3, L equal to 1, M equal to minus 1, and MS, spin quantum number of the electron, is plus half. If L is equal to 1, then it denotes p orbitals which are present in the third shell. So it denotes 3p orbital electron. So now we have 3d, 4p, 4d, 3p orbital electrons. Therefore, the correct increasing order of their energies would be lowest in energy 3p, then comes 3d, followed by 4p, and highest in energy would be 4d. Option 2 shows the correct increasing order of the energies of the electrons. That is S, P, Q, and R. S less than P, less than Q, less than R. In the same slide, I have included another question, that is question number 13. The number of radial nodes for a 4p orbital is dash. You'll have to fill up the blank space. The number of radial nodes for any orbital is determined using the formula n minus L, principal quantum number minus azimuthal quantum number minus 1. So, for a 4p orbital, n is equal to, principal quantum number is 4 and azimuthal quantum number is 1. So, the number of radial nodes for 4p orbital will be 4 minus 1 minus 1. So 4 minus 2, which is 2. Therefore, the number of radial nodes for a 4p orbital is 2. More about radial nodes and total number of nodes and what are nodes, what are nodal planes, we will see in the next part 2 of the structure of atom. Question number 14. Identify the two incorrect statements from the following. Statement A. The existence of Bose orbits or energy states, we can also call them as stationary states. The existence of Bose orbits is experimentally supported by hydrogen spectrum. B. The total number of nucleons is called as mass number of an atom. C. Tritium 1T3 is a newly discovered element with mass number equal to 3 and Z equal to 2. D. According to Rydberg, all series of spectral lines in the emission spectrum of hydrogen can be described by the expression frequency nu is equal to 109,677 into 1 by n1 square minus 1 by n2 square, where n1 is equal to 1, 2, 3, 4, etc. and n2 is equal to n1 plus 1, n1 plus 2, n1 plus 3, etc. So, from these statements, we have to pick out two incorrect statements. If you look at these statements, C and D are incorrect statements. Tritium is not a newly discovered element. It is not. It is an isotope of hydrogen with mass number equal to 3 and Z value equal to 1. Z value is equal to 1 and not equal to 2. I have shown it in the form of a picture here. The isotopes of hydrogen are protium, deuterium and tritium. Protium has one proton with one electron in the n equal to 1 energy state. Look at deuterium. One electron is there in deuterium and tritium also, but inside the nucleus in deuterium there is a proton and a neutron. So its mass number would be 2. For which one? For deuterium isotope. And for tritium isotope, the electron outside in the first energy state is the same, 1. But the nucleus contains 1 proton plus 2 neutrons. So its mass number is 3, but its Z value remains the same as 1. In all the 3 isotopes, the number of protons remains the same as also the number of electrons. So statement C given is wrong. The corrected statement is given. Then statement D is also wrong. According to Rydberg, all series of lines in the emission spectrum of hydrogen can be described by the expression wave number, not frequency, wave number nu bar, which is equal to 1 by lambda is equal to 109,677 into 1 by n1 square minus 1 by n2 square, where n1 is equal to 1, 2, 3, etc. and n2 is equal to n1 plus 1, n1 plus 2, n1 plus 3, etc. I have shown a picture of the emission spectra of hydrogen in various series of spectral lines: Lyman series, Balmer series, Bastian, Brackett and Fund series of spectral lines. These spectral lines are an experimental evidence to support the existence of Bohr's orbits, and also Rydberg's equation, where nu bar is equal to 109,677 into 1 by n1 square minus 1 by n2 square. Question number 15. It's the last question of part 1. The de Broglie wavelength of an electron in the third Bohr orbit is dash. So we need to find out the wavelength of the electron in the third Bohr's orbit. We have to make use of two mathematical expressions here. First, de Broglie wavelength of an electron. We know it to be equal to lambda is equal to h by mv. We know m is the mass of the electron, v is its velocity, h is Planck's. I don't have to explain all this again. So it is labeled as equation 1. Now, based on Bohr's postulate, we know that angular momentum of an electron in an orbit, or the angular momentum of an orbit itself, is quantized and given as mvr is equal to nh by 2 pi. So rearranging, we get it as mv is equal to nh by 2 pi r. On substituting the value of mv in equation 1, which equation? Lambda is equal to h by mv, we get lambda is equal to h divided by nh by 2 pi r. 2 pi r will come to the top numerator, h and h gets cancelled, so we get lambda is equal to 2 pi r by n. That is equation 2. Here, r is the radius of the orbit in according to Bohr's model of an atom, and that r is given as n square a0 by z, where a0 is the radius of the first Bohr's orbit of hydrogen, a0. So the radius of any other orbit is got by using the formula r is equal to n square a0 by z. Substituting the value of r in equation 2, which is equation 2, lambda is equal to 2 pi r by n. That is equation 2. So we get, therefore, lambda is equal to 2 pi n square a0 divided by n already is there into z. N and n square will get cancelled, so one n remains. So we get lambda is equal to 2 pi n a0 by z. For hydrogen, z is equal to 1, atomic number is 1, and we are asked to find out the de Broglie wavelength lambda for n equal to 3 electron. So substituting the value of n as 3, we get lambda is equal to 2 pi into 3 into a0 by z, which is equal to 1. 2 into 3 is 6, so we get 6 pi a0. Now, since pi is 22 by 7 or 3.14, we get lambda, the de Broglie wavelength of an electron in third Bohr's orbit, is 6 into 3.14 a0, which is 18.84 a0. So that is the de Broglie wavelength of an electron in Bohr's third orbit. We have completed 15 questions in this session. More we will be doing in part 2. So I just added a footnote, that is my colleague Parshuram Bellari sir, who's an IT expert, and me, KG Sujaya. I'm the author of the contents of this, of all the chemistry topics, units which we are dealing with. We would like to express our gratitude to all our viewers and subscribers of the channel Sujaya Chem Classes. Our request rather, would be to all students to share the contents of our channel with more and more students. It is totally free for all, but if you go through the contents, you will find that it is loaded with information and thought-provoking contents for children, particularly of classes 11 and 12. So I request all the children to make the best use of all the contents which we are going to post or which we have already posted. And thank you.